September 1997, and the eyes of the world are focused on the little town of Gerlach in Nevada's Black Rock Desert. Locals call it the town conveniently placed in the middle of nowhere. The only excitement is usually when freight trains pass by. But today, it's the desert which is arousing the real interest. It boasts a rare feature, a unique surface, a 13-mile long strip that is to become the setting of what is being called the greatest race of the century. In a head-to-head challenge between American driver Craig Breedlove and a British team headed by Richard Noble, their aim to smash through the sound barrier. This is the story of Richard Noble's team and their bid to build the fastest car on Earth. Richard Noble is the current land speed record holder. In 1983, on that same Black Rock Desert, he drove his car thrust 2 at 633 miles per hour, creating a record which stands to this day.
Now, the thing about it is, the land speed record is frankly the most exciting thing you can do on God's earth. I mean, you know, I try to do most things in life, but this just beats everything. It produces the most enormous challenges, like, you know, finding deserts and getting different countries involved and so on and so forth. And the other thing, which is the most crucial of all, is the teamwork side of it. To be able to work with a very, very gifted and skilled and communicative and exciting group of people is crucially important. The other thing too is that if you've actually got the land speed record at whatever it was, 37 or so, there's a great danger that your life might have actually peaked at 37. And you know, and you say, well, how the hell do you follow that? You know.
But follow that he did, and in 1993, entirely by chance, Noble met Ron Ayres, an aerodynamicist, and put to him a proposition which would change their lives. He asked him to design a car capable of breaking the sound barrier.
Well, the first thing was to say, this is totally ridiculous, it's much too dangerous, you could never do it. And I only carried on working out of curiosity to decide, well, if someone was idiot enough to try and travel at supersonic speeds on land, what would the car look like?
Ayres started to produce drawings which were not the usual perception of a record-breaking car.
It seemed very clear that the centre of gravity, the centre of weight of the vehicle has got to be well forward. Now, to achieve that, you can do it very easily with 2 engines because you can put one each side of the driver, but with only one engine, which has got to go at the back, then difficult compromises have to be made. So 2 engines for stability, not for performance.
Ayres was also acutely aware of the need to understand fully what happens to the airflow around and, more crucially, under the car at supersonic speeds. Drawing on the power of highly complex Cray computers, the team began to build up a picture of their proposed model by what is called computational fluid dynamic assessments. But Ayres had some reservations.
It's got to be stable. If something goes wrong on this vehicle, it goes wrong so fast it's virtually instant oblivion to the driver. So inherent stability is an absolute essential, and if we ever feel that we haven't got that, we stop the project.
The speed of sound varies in different parts of the world. At Black Rock it is 747 miles per hour. So to determine the stability of thrust, a series of wind tunnel tests were conducted. For the perfectionist Ayres, who used to design guided missiles, this was still not enough.
We had to represent ground moving at more than 800 miles an hour under the wheels. You can't do that in a wind tunnel without having a conveyor belt of 800 miles an hour. And that would be even more difficult to design than a supersonic car. So we evolved a technique of our own and totally new, where we said, okay, if we can't blow air over the model, let's see if we can move the model at supersonic speeds and control it.
In a leap of lateral thinking, Noble enrolled the services of the experimental establishment at Pendine. More used to testing missiles, they harnessed a scale model of thrust to a rocket sled and prepared to fire it down a rail at 850 miles per hour. By studying frame-by-frame footage of the Pendine tests, Ayres was able to prepare an analysis of the airflow and draw up an accurate prediction of the car's behaviour.
You can just see shock waves over the nose and etc. So we really were going at supersonic speeds, missing the ground by less than a millimetre. And the results from these experiments tied up incredibly well with that computer method. And that's what gave us the confidence that we really could design this vehicle and we really could keep it on the ground.
Keeping it on the ground is the big problem. When Noble broke the land speed record, the airflow over his cockpit was supersonic. But what exactly happens to a car when it reaches that sort of speed? The speed of sound is determined by altitude and temperature. When an aircraft goes faster than the speed of sound, it creates air pressure which builds up into a cone-shaped shock wave. At height, this wave is dissipated. When thrust goes through the sound barrier, what will happen to these shock waves? Will they be dissipated, or will they bounce against the ground and lift the car, with catastrophic results? No one really knows. Ron Ayres thinks he does, only he's not saying.
There are features that might well have application, but we would rather kind of keep those to ourselves. Where we believe we've kind of genuinely invented something, we'd rather prove them to our own satisfaction before we start proclaiming them to the press and certainly to our competitors.
You see, the extraordinary thing is that Ron, as a result of all Ron's work, he ended up producing a simple piece of paper which said we could produce the world's first supersonic car. And when you've got a piece of paper like this, you've got to do it. I mean, you can't, you know, it's a once-in-a-lifetime opportunity. People don't get these sort of chances, and you've got to go for it.
And go for it they did. With the design proven, one major obstacle remained: the steering. Putting the wheels at the front would have spoiled the streamlined shape, so another solution had to be found. It came in a novel way, a 30-year-old Mini with rear-wheel steering.
The arrangement of the wheels on the Mini is an exact scale model of the full-size jet car. That was essential that we did it that way, and we did it accordingly. Between the frames, it's only 26 inches. That's the only space that was available, so the wheels had to have this offset stagger to get the suspension and steering in. The reason why they do not track each other is because the leading wheel will break up the desert and the second wheel will have nothing to adhere to, so they're set sideways for that reason.
When I first started to drive it, it was all over the shop, and it's a very funny sort of feeling, you know. You're driving along, and if you're turning left with a normal car, you turn left and you go left. But with a rear-wheel steer car, what happens is you turn left and you go right and then you go left, all right? So it takes a bit of getting used to. However, once we got going with it and once we got it really sorted, I found I could drive that car to an accuracy of 1 inch at 90 miles an hour. And really, at the end of the testing, we came back and we said, you know, it's absolutely straightforward. It's going to be all right. That cost us total cost of 600 quid. Brilliant.
February 1995, and construction on the 54-foot-long vehicle had begun in earnest. Everything seemed to be finally in place, except for one vital element: the driver. In the past, the drivers have tended to select themselves. Was this to be Noble himself?
The reality is that I'm faced with a situation which is really very clear, that we have really quite a sizable project here running now. There is absolutely, I'm responsible for running this project and also for financing this project. And there's absolutely no way that I can get myself fit or well or anything to drive this car.
So how do you go about selecting a driver for a record-breaking car? Through a magazine advert, 16 hopefuls were selected and put through a battery of personality and intelligence tests. Right from the onset, Noble made it clear he was looking for a team player, not a prima donna. Desert conditions dictated that the ability to endure temperature and tiredness was vital, so the candidates were kept awake in a specially heated room and their behaviour observed.
It's just on 8 o'clock in the morning now, Tuesday morning. They've been in there since about 3 o'clock yesterday afternoon, so that's about 17 hours. They haven't slept in that time, at least they weren't supposed to sleep in that time. They were told that it was up to them to keep themselves awake. One of them has been asleep reasonably properly, and one or two of them have been looking pretty close to it as well. Interestingly enough, they didn't do the team thing and wake each other up and just let each other go to sleep.
Finally, the successful applicant was announced. It was Andy Green, a 32-year-old RAF fighter pilot. More used to flying Tornadoes, Green was now ready to throw himself into his new role.
When I was told that I was going to be the driver last week, Richard presented me with the key to the car. It is the key to the world's most powerful car ever to be built. That is tremendously exciting, and I get a great deal of excitement and pleasure from that concept.
By April 1996, with the superstructure completed, Noble moved the organisation to a hangar at the Defence Research Establishment in Farnborough for fitting out.
Well, we've been here about a week now, and basically we've got a front suspension problem which we've got to sort, and also we're doing the fuel pipes and the fuel leads. So once we've got those in place, then of course the car goes forward, and the finishing off of the car is relatively straightforward because all the bodywork and so on is already done. But the thing to understand about these cars is that they're experimental racers, and they're always in bits. So we've designed this car so it takes the bits very, very quickly, very easily, and that means effectively that we minimize the amount of time on development work on the car on the desert with it in bits, and we can maximize the running time.
Running times cost money, and so do the workforce. But Noble had a unique way of raising funds to keep the project going.
Finding one sponsor after the next is a complete nightmare. On top of that, the sponsorship thing tends to be very political within the companies for obvious reasons, and therefore it makes them very unstable forms of finance. So therefore you need something else, and so we've set this thing up with in such a way that around 60% of the money coming into the project comes from trading.
All of Noble's team had to learn the art of trading, and that necessity is the mother of invention.
See if the old boy network still works. Hello, who's speaking? Oh, hello Chris, it's Martin Davison from Q-Shed. Hi, do you have in your workshop a milling machine?
With the delays came the frustrations.
There is a plan, and the plan has to be adhered to, really. For the assembly of the car, there's drawings, there's a pattern, there's a plan. But as with any new build for anything, whether it be an aircraft, car, boat, nothing's going to fit the first time. There's going to be loads of problems.
I'll do that. Nails. We're going to nail this sucker together.
Parts of it down here are running into the tube when it's fitted, and that's basically it. So we're waiting for the Shoebury engines to come. It's coming at lunchtime, and we'll fit one of the Shoebury engines to see whether we've got a similar problem.
You don't design a thing like this in great detail before you start. You have the overall design, and then a lot of it is designed actually over the vehicle when you're putting things on. That's when the detail design is done. This is, apart from being a final product, it's also a first prototype, so that when you start putting it together, then you find out whether it's exactly as you expected it to be. And, okay, so you have modifications to make. That's what engineering's about.